Okay, so today is our real first lecture of Introduction to Real Analysis. The first day of class, I kind of reminded you of set theory, notation, the basic operations. But today we're going to really start getting closer to the actual topic of real analysis. In particular, we're going to talk about functions today, the notation that we'll be using, and the way that we're going to think of functions in this class. Now, I know all of you as math majors are very familiar with functions, but it's still important that in the textbook that you do read the section on functions and pay attention to the way things are defined, because especially with this textbook and many real analysis textbooks, actually, there's different notation that different textbooks will use, and to really make sure that you understand reading later on in the book, you have to start kind of early and look at like what are the fundamentals that they're using and how are they defining things. So today is going to be just looking at functions, definitions, and notation. And we'll maybe prove like one or two things. Okay, so this is functions. Okay, so before defining a function, I'm going to remind you of one more set operation. So definition. Okay, so if A and B are sets, then the Cartesian product lowercase b here is the set A times B, which is equal to the set of all ordered pairs AB such that little a is in capital A and little b is in capital B. Okay, so this is the Cartesian product. Okay, so let's just do some examples of it to remind ourselves of what this is. So maybe let's say that A is equal to the set of 1, 2, and 3, and B is the set maybe 1, 4 or something. Yeah. So then the Cartesian product A times B is going to be the set of all ordered pairs, where the first entry from the ordered pair comes from A, and the second entry comes from B. So the ordering of this product does matter. You'll get a different set if you do B times A. But here we have A times B, so this will be 1, 1, and then 1, 4, and then 2, 1, 2, 4, 3, 1, and 3, 4. Okay, so this is with a discrete collection of sets. So these are discrete sets here, but we can also look at Cartesian products of continuous sets, the real number line. So maybe we can say, so I'll call this like example 1, call this maybe example 2. So maybe A is the set of all real numbers. So X is a real number, such that let's just say 1 is less than or equal to X, which is less than or equal to 2. And then we'll say maybe that B is the set of all Y, maybe, such that 0 less than or equal to Y, that's going to equal 1, or 2 is less than or equal to y less than or equal to 3. So then we can ask ourselves, what is this set A times B? Okay. Well, these are infinite sets, uncountable sets. We can't really write it out like we did with these discrete sets up here. But we can draw these sets in the plane. And so recall that, so like the Cartesian plane is just R cross R. So each point in this plane is an element of R times R. Right? So A times B, since A is a subset of R and B is a subset of R, A times B is going to be some subset of points in this plane. So let's just say 1, 2, 3, 4, 1, 2, 3, 4. Let's look at A. So A is the set of all x that are in the interval 1 to 2. So it's like here's A, right? So every element in A belongs in here. So I'll go ahead and write down the numbers here. So 1, 2, 3, 4. And then this is 1, 2, 3, 4. Okay. And then y, so this would be our y-axis up here. And this would be our x-axis. Ugly y. Y is this set here where it's all y that satisfies 0, 1. So it's all y in this interval here. Or it's the collection of y that satisfies being interval 2 to 3. Okay. So, all right. So 0, 1, 2, 3. So, okay, what are the ordered pairs here? Well, one element, you can take 1 from A and pair 1 with 0 from Y, right? And that would be that element right there. 1, 0. That's that ordered tuple there. You can also take 1 from here and then that one right there. So the ordered pair 1, 1 is going to be in there, and that's right here. Right? But also, just fixing x to be 1, you can take every y between 0 and 1 as well, right? And each one of those y's is going to give you another tuple. And if you connected all of them together, you would have that line right there. Right? But then you could do the same thing for 2, like fix x at 2, and then take everything in the interval 0, 1 from there. So you get that tuple, 2, 0, and then you get 2, 1, and then everything in between. Right? But then you can do the same thing. You can fix y to be 1 and then take every x between 1 and 2, and you get that. And then do the same thing if you fix y at 0 and take every x in between there, you get that. And you can do that all the way across. So that's one piece of the Cartesian product of that set A and that set B. But then you can do the same thing for all y between 2 and 3. So you have fix x at 1, 1, 2 is in that Cartesian product, 1, 3 is also in that Cartesian product, and everything in between them. And if you do that again, fixing x at 2, like that, and then So this right here is A times B, or A Cartesian product B. Okay. Does that sort of make sense?
Yes.
Okay, so now that we have our definition of Cartesian product, we're going to define a function in terms of Cartesian products. So, all right, so definition. Okay, so let A and B be sets. Okay. So a function from, well, yeah, from A to B. Often written as F right arrow A B. Okay. Is a set F of ordered pairs in A Cartesian product B. Okay. So that for each A in capital A, there is a unique little b in capital B, so that I don't like saying so that so many times, I'll say with a unique b in capital B, where A comma B is in that set F. Okay. Maybe not with, where, maybe with would be the best way to say it. Okay, so this is the definition of a function that we're going to use. Okay. So under this definition, we're also going to introduce the terminology. So we're going to also say that F maps A into B. Another way of writing that. Okay. All right, so suppose we have like some set A. Okay. And we have some point in here, call it maybe some element, call it little a. Okay. And then we have some set B. Okay. Then for every element over here, we're going to have some element that's mapped over here with elements of B. So F looks like this. And this element right here, that right there is B equals to F applied to A. And then this right here this is called the range of f. So this is bar of f. And I'm going to describe that notation in a moment. And then this set here, this is denoted by d of f. All right, so let me go ahead and finish this definition off over here and tell you what these things mean. So, see if I can fit it right here. The set of first elements from F is the domain of F written df like that. And the set of all second elements is the range of F. And that's written R. Okay. So it's important to note two things. For this function definition here, d of f is equal to a, but the range of f is, the best we can say, is a subset of p. Okay. Your textbook doesn't use this terminology, but P is sometimes called the codomain, which is not the same thing as saying the range. Okay. So. Right, so just observe that we have new notation there and there, which you know what the domain and range typically are, right? I'm sure that you all do. But the definition of F is a little bit different than what you're used to. It's just a subset of the Cartesian product between two sets. Okay. So let's look at maybe some examples. All right, so this will be the example number 3 maybe from today. Let's say, what example did I have? Say, let F map R be defined by, let's say, f of x equals to x squared. Okay. So, so what are these? So what does the set look like? So the set F looks like, say, 0, 0's in there, right? What else is in there? 1, 1. 2. Well, let's just say positive real numbers, just so I don't have to draw so much or think about the negatives. 2 4's in there. And then like, what else is in there? There's all kinds of things, right? Like 1/2, 1/4. There's an uncountable number of things in there. Right? So if we look at R, right, times R, right? So okay, so like that tuple's in there. Like this, and we know what the graph is going to look like. We start plotting all those points inside of F. We plot all those, we get this curve, right? So okay, so this tells us, so like, okay, our domain is going to be like all of that, right? So D of F is going to be equal to R plus, right? Now, if we look at all the Y values in there, right, all the second values, it's just everything. So the range of the is going to be R plus as well. Oh, so R plus to R. Okay, so but notice like if this is like your A and that's your B, right? Then the range is strictly contained in B. Okay, so let's move on to our next definition. Okay, so definition. So let F map A to B, and let E be a subset of A. Okay, so the direct image of E under F, okay, is the set, say, F of E, which is a subset of B, defined by F of E equals to the set of all F of X such that X is in E. Okay, so this is the direct image of a subset of the domain. Okay, so if we can, maybe I'll draw a picture. So this is A, and let's say that, so everything in A is going to be mapped over here to B somewhere. Call this set B. If I pick some subset in here, well, there is an image of A. So the range of A is somewhere in here. Maybe it's like this. So that's let's say that this is the range of that right there. Okay. But then if we have some subset in here, maybe like call this E right there, then the direct image of E is just the collection of all the points in here that were mapped under F. So maybe like here, that'd be F of E. So basically, it's just another way of thinking about this is just restricting your domain to be some subset of the original domain, and then looking at what F does to that subset. Okay. So let's continue on with this definition. I guess this would be a new definition, maybe. So if H is a subset of B, then the inverse image of H, so inverse image of H is F superscript minus 1 of H equals to the set of all X in A such that F of X is in H. Okay, so this is the inverse image. Okay, so if you have maybe, so like if you take a set here, H, right, then the inverse image is the set of all things over here that got sent to H. Okay. Give you a moment to write that down. And if at any point in time you need me to stop and like explain the definition, just let me know. Okay, so let's look at some examples here. Okay, so for example, I'm pretty sure. So let's say let F map R to R be defined by F of X equals to X squared. And let say E be defined as the set X such that 0 is less than or equal to X, less than or equal 2, and G equals to the set of all y such that 0 is less than or equal to y, which is less than or equal to 4. Okay. Okay, so we're taking E to be in this set and G to be in that set. Okay? Just by the X and the Y, it just kind of implies it right now. Okay? So what is the direct image of E? Well, the direct image of E is the set of all y such that 0 is less than or equal to y, which is less than or equal to 4. So our function is defined by just squaring the entry. So if we look at everything inside there, so every x in there that's possible, and you square it, it'll satisfy this property, right? So everything in here belongs to this set. It has to. Because if you're in there and you square it, then you're at least 0 and at most 4. So notice, though, this is important to notice. Notice that the direct image of E is equal to this set G. This happens to be the case that we defined them in such a way. Okay. Okay, so let's look at the inverse image of G. What's that set? Well, the inverse image of G is a set of all x such that -2 is less than or equal to x, which is less than or equal to 2. And this set does not equal E. You see that? So like, what are all the possible values in R that get sent to that set? Well, clearly if x is in this interval here and you square it, it's going to be in that interval there, right? However, if x is in the interval -2 to 0 and you square those numbers, you're also in that interval. So the inverse image of G is this, which does not equal E. Okay. So in particular, this is a caution here. F inverse of F of E does not have to equal E. So this is in general. Okay. You'll see that, right? We applied, so F of E is actually equal to G, right? The direct image of E is equal to G. But if we look at the inverse image of G, it doesn't equal the set E that we started at. There's more possibilities. Right? And if you looked at the graph of this, you'd see that, right? So 1, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 4, right? So what is our set E? And so this is an X, this is Y, right? So what is our set E? It's all of these X here. That's our set E. What's our set Y? 0 to 4, right? So right? And f of x is defined as x squared, right? So for what values of x, if we square them, in this interval? Well, values here also get mapped to values in there. If you pick anything in here and square it, it's going to have a value somewhere inside of that interval. Right? So basically, you're looking at ordered pairs x squared. Right? For what ordered pairs does this satisfy the case that this entry here is at least 0 and at most 4? All values of x that make that true. So E does not equal all of the values that are possible. Okay. So this motivates the following definitions. It's not always the case that the inverse image of the direct image equals the original set. However, what types of sets satisfy this? What types of functions satisfy this? Okay. Okay. Oh, before we get to those definitions, we should maybe observe something. I have a claim here. So if F maps A to B, where G is a subset of B, and H is a subset of B, then the inverse image of G intersect H is a subset of the inverse image of G intersect the inverse image of H. Okay. So whenever we're proving subsets, right, we do this element argument, right? We take an arbitrary element over here and show that it has to exist over there as well. So let's go ahead and prove it. Okay. So let's let X be an arbitrary element of the inverse image of G intersects H. Okay. Now, if it's in here, then okay, we have a definition, right? So what is this set? Well, this is the set of all A that are in the domain, right? Such that F of A is in this set. Now that's just applying the definition of the inverse image, right? This set is equal to that. Whatever is right there goes right there. Okay. So in particular, we know that F of A is an element of that intersection. So This implies that f of A is an element of G intersect H. And so f of A is an element of G, and f of A is an element of H. Okay, so if f of A is in G, right, what does that mean? Oh, f of A is in H as well. Well, that means that A is in the pre-image of H, and A is in the pre-image of G. So by definition, A is in the pre-image of G, and A is in the pre-image of H. Hence, A is in the intersection of these sets. And that should end the proof. Okay. So it's left as an exercise to show that that is actually a subset of that as well, which means that they're equal, right? If they're subsets of each other, then they're equal. So this is one of those things where if I put a star by it, there's a chance it might appear on the exam or something. So what about this question here? So is this a subset? This one. Okay. So take a moment to write that down just so you can try it on your own. All right, so let's continue. Okay, so another definition. So let F map A to B. All right, so this is a three-part definition. So if x1 not equals to x2 implies f of x1 is not equal to f of x2, then f is called a injection. Injection. Okay. Actually, let me fix that. There's a few different ways to say it. You can say injective or injection. I'm going to say F is called injective. Injective. be if the range of f is equal to b. Again, these are sets we're talking about here. Then f is called surjective. Surjective. In part C, if f satisfies A and B, then f is called bijective. Okay. Now, all of you are familiar with these definitions. Another way to think of injective is 1 to 1. Surjective is same thing as saying onto. And bijective is 1 to 1 and onto. But as we enter into like our upper level mathematics courses, you're going to start dropping 1 to 1 and onto and begin using injective and surjective more often. So I'll give you a moment to finish writing that down. Be sure to have these definitions like clear in your head that injective means two values in the domain. If they don't equal, then their images don't equal, right? Okay, so let's prove a little claim. Am I good to go?
Yes.
Okay, claim. If f maps A to R is defined by f of x equals to 2x over x minus 1. I'll write it cleaner than that. Maybe like this, x over x minus 1, where A is equal to the set of all x such that x is not equal to 1, then f is injective. So that's the claim. So basically, we just have to show that it satisfies the definition of being injected, right? So I'm going to put my scratch work over here. So what do we want? We want that if x1 doesn't equal x2, then f of x2 is not, or x1 is not equal to f of x2. That's what we want, right? But this is like this statement is similar to a proposition if P then Q, right? And we know that the implication P implies Q is equivalent to the contrapositive of that statement. So we know that that's logically equivalent to not Q implies not P. Okay? Where this is P right here, and this is Q. So an equivalent way of showing that the definition of that F is injective is to take this and just show the contrapositive of that definition is true, which is we want equivalently that if f of x1 is equal to f of x2, that implies x1 is equal to x2. That is the same, these are logically equivalent. That's just the contrapositive of that. Okay? So suppose f of x1 is equal to f of x2. So this is not proof, that's just like scratch word. This is the actual proof of it. So if f of x1 is equal to f of x2, so maybe hence, we know that 2x1 over x1 minus 1 is equal to 2x2 over x2 minus 1, right? Now, because this is my nice proof over here, I'm going to come over here and do a little bit of scratch work to kind of simplify the algebra. So if that's true, and we know that neither one of these, so we know that x1 not equals to 1, and we know that x2 not is equal to 1. That's important because if you're dividing by 0 and then you try to like algebraically manipulate this, you're going to get something that could be incorrect or is incorrect. So I'm going to fix this proof in a moment because we need to observe that as well. Okay, so I'm just looking at that equation there. So then 2x1 times x2 minus 1 is equal to x2 times x1 minus 1. And again, this is just my scratch work over here. We can divide both sides by 2. We get that x1 times x. Yeah. Okay. So then x1, x2 minus x1 is equal to x1, x2 minus x2, right? Just distribute in. But notice now this is the same thing as this. So you can subtract on both sides and you get the minus x1 is equal to minus x2, which implies that x1 is equal to x2. Okay, so let's go ahead and write out our formal proof now. So, and we have all of our scratch work right there. So, so suppose that. I'm going to give myself some more room by erasing this, but hopefully all of you see the algebraic steps are clear and you should know what to do now. So let's just suppose that. And so we know that two x1 over x1 minus 1 is equal to 2x2 over x2 minus 1. All right, so then we can say since xi is not equal to 1 for I in this set. So now I'm doing something a little bit more fancy that you're not used to. Instead of like individually saying x1 and x2 not equal to 1, I use a subscript and I say that xi doesn't equal 1 for I in that set. Hopefully that makes a little bit of sense. So since that, we observe that, say, 2x1 times x2 minus 1 is equal to 2x2 times x1 minus 1. Okay. So now actually, if I was writing up this proof, I would probably start centering it in my paper. So let me see if I can rewrite that just a little bit nicer. So I'm going to try to squeeze it in here. Okay. And then I always put these double arrows whenever an equation follows from another one. And then divide both sides by 2, and then multiply in. Go. Double arrow. These quantities are the same. Good, 2. Okay. And then one more. Just finish it off. So if that is equal to that, then the inputs have to be the same. So that claim is true. Okay. All right. So I should maybe add a problem for you to think about for this claim. So for what H is subset of R, and I'll say B. For what set B, which is subset of R, is this F bijective on so it's clearly, we've proven it to be injective. So if you want it to be bijective, we want it to be also a surjection, right? So there is some subset in R that will make it also onto when you find that set. So what is that set? Okay. Okay. So then one more definition and then we'll call it a day. Okay, so definition. So if the mapping from A to B defined by F, if that is a bijection, then F superscript 1 equal to the set BA such that, well, BA is abbreviated like that, such that AB is in the original function F. So if that is a bijection, then this is also a function as well. Called the inverse of that. So one way of thinking about this, so if that is a bijection, then for every pair in F, right, not only is B the unique element associated with A, but A is also the unique element associated with B. Right? That's what happens if it's injective. In the sense that it's surjective, everything in B appears in, every element of capital B appears in one of these ordered pairs from F. So then you can define a function from B back to A with this. Okay, so we have some set A, and some set B, and you have F, which is a bijection. And if this is A, and this is B equals to F of A, then A is not only uniquely associated with B, but B is uniquely associated with A. Nothing else over here is mapped to it. So we can define an ordered pair by just sending it back. Okay. So I think that we're running a little bit out of time, so let's just call it a day here. So as far as homework problems to look at, which I'm not going to pick up right now, I'm just assigning them for you to do, to look at. Let's say from section 1.1, look at problems 1 through 17. So, section 1.1, say 1 through 17. So this is your suggested homework for the weekend. Okay. All right, so any questions?
Page what?
So section 1.1. So the problems start on page 10. All right, well, I guess there's no questions on that. Just be sure to try these problems. So next week when we meet, if you have any questions over any of those problems, you can bring them up in class and they can like work through the solutions. All right, y'all have a good day. Stay safe. And that'll be it. I'll see you next week.
Thank you.
Thank you.
Have a good weekend.